In this video, I'm going to show you how to calculate confidence intervals for population standard deviation and population variance. I'll be looking at a couple of examples taken from section 9.4, and I invite you to join me on page 500 and 501 in the text. Now, you might have noticed the title of the section is Confidence Intervals for a Population Standard Deviation. But when you look in the formula box that you see right there at the top of page 500, that little purple box, it's talking about confidence intervals for sigma squared, aka population variance. So you might wonder, well, where would you find the confidence intervals for the standard deviation? Well, there's some text right below the purple box right there. It helps if you recall that the standard deviation is the square root of the variance. So as it says right there below the box, if you need a confidence interval for sigma, aka population standard deviation, you just take the root of the lower bound and the upper bound that you see there in the box. Now, unfortunately, there's no built-in function in the calculator for this particular type of confidence interval, so you have to do these by hand more or less, and you need to get some values from the chi-squared table. Now, there's two values that are needed every time. I call them chi-squared left and chi-squared right, but in the text they're called differently. Chi-squared left is the one that you see in the text is chi-squared 1 minus alpha over 2. It's the smaller of the two values. And chi-squared right would be chi-squared alpha over 2, the larger of the two values. I just find that it resonates better for me when I call them chi-squared left and chi-squared right, because they are found that way in the table. Another piece of advice, it's very common to see people making errors of arithmetic when they're calculating these intervals. What they typically overlook is whether the problem supplies them with the sample standard deviation or the sample variance. And you'll notice that the formula, the one that you see in the little box on page 500, it calls for the sample variance, aka s squared. So all too often what you see when you're looking at people's work on exams or whatever is that they are squaring when they're not supposed to square, and they're not squaring when they're supposed to square. So just be sensitive to that. It shouldn't be an issue. First up, we have number 10. It says a simple random sample of size n is drawn from a population that is known to be normally distributed. The sample variance, s squared, is determined to be 19.8. Part A, construct a 95% confidence interval for sigma squared, aka population variance, if the sample size n is 10. Well, the first thing you have to do is go to the chi-squared table and find out what are the values chi-squared left and chi-squared right. If you look them up in this case, you should be going with 2.7 for chi-squared left and 19.023 for chi-squared right. You want to make sure you get those, and if you need some help with that, this section contains an extensive write-up on how to navigate the chi-squared table. Anyway, we are given the sample variance in this case, so we don't need to square, and let's calculate the lower limit for our confidence interval. You take the degrees of freedom, which is 9, 10 minus 1. You multiply by the sample variance, which is 19.8, and then you divide by chi-squared right. It's the larger of the values. So in this case, 19.023. And there's your lower limit. Now that's the one downfall to using chi-squared left and chi-squared right, because chi-squared left is the smaller of the values, and it ends up being used in the upper limit of the confidence interval. In other words, the right-hand limit of the confidence interval. So anyway, don't be confused. We need the upper limit as well, and we might as well recycle our key sequence here. All we have to change is the denominator. So I'll change that to 2.7, and then I'll delete the extra digits. And there's our upper limit right there. Part B says construct a 95% confidence interval for sigma squared if the sample size n is 25. Well, now that we've changed our sample size, we've also changed the degrees of freedom, and that means you have to go back to the chi-squared table, and you have to find two new values for chi-squared left and chi-squared right. In this case, if you locate the correct ones, chi-squared left would be 12.401, chi-squared right would be 39.364. And our lower limit would be as follows. We take the degrees of freedom, which is 25 minus 1, aka 24, multiply by the sample variance, and divide by chi-squared right, 39.364. And so the lower limit would be that. Let's recycle this key sequence to get the upper limit. The denominator would be 12.401. So there's your upper limit right there. Part C is asking for a 99% confidence interval for sigma squared if the sample size n is 10. They want us to compare the results with those obtained in Part A. Now, half of Part A is off the screen right there, but you can see the upper limit right there is 66. Again, you have to go back to the chi-squared table. Degrees of freedom have changed, and the confidence level has also changed. So the values would be as follows. Chi-squared left would be 1.735. Chi-squared right, 23.589. So the numerator would be 9, that's degrees of freedom now, times 19.8. And for the lower limit, we want to divide by 23.589. So there it is. And for the upper limit, let's just recycle the key sequence. And we'll change the denominator to 1.735. I'll delete the extra digit. There's the upper limit. Now you notice that the interval is a bit wider than the one we obtained in Part A. And we would expect that because the confidence level has increased. If you recall, we've talked about this before, when you increase the confidence level, contrary to your intuition, you make the interval wider because you're basically asking the interval to accommodate a greater amount of variability. You're asking the interval to capture the true mean 99% of the time as opposed to 95%. So naturally the interval would be wider. And just to reiterate, we've kind of seen this before, but it's always good to remind people, if you increase the sample size, you decrease the width of the confidence interval. If you increase the confidence level, you will increase the width of the confidence interval. So you can look at that carefully and figure out all the permutations. Next up, we have number 12 here, and this one is it appears to be a data-driven problem, but in reality it's not, because we're given the sample standard deviation right there in the problem. Now they're asking in this case for a 95% confidence interval, and if you'll notice, there are 10 values in that data set right there on problem number 12. Let's read it. It says battery life. The following data represents the battery life in hours for a random sample of 10 full charges on a 5th generation iPod music player. In problem 24 from section 9.2, it was verified that the data are normally distributed in its S, sample standard deviation, equals 2.14 hours. Construct a 95% confidence interval for the population standard deviation of battery life in hours. Interpret the interval. Well, basically it's the same formula, except that we're going to be taking the square root now, because we're looking for an interval for standard deviation as opposed to variance. So first thing we have to do is go to the chi-squared table, and if you do, you should get a feeling of deja vu, because we're using the same two limits that we used in Part A from the previous example. Chi-squared left would be 2.7, chi-squared right would be 19.023, and because they've given us the sample standard deviation here, we have to square. So the lower limit would be as follows. You take the root, and you just use an opener here. Now, my calculator has a bug in the emulation software, and normally on this calculator you don't see the radical extending over the parentheses like this, but it does here. Anyway, the numerator would be 9. That's the degrees of freedom. You'll notice there's 10 values in the data set there, so 10 minus 1. And then we need to multiply that by the sample standard deviation and square it. So we put in 2.14. And let's square that. And then we need to divide that by, for the lower limit, chi-squared right. So 19.023. Anyway, there's the value. And then for the upper limit, let's recycle our key sequence. And all I have to do is edit that denominator. I'm going to change it to 2.7. And I'll delete the extra digits that are there. There's your upper limit. They ask us to interpret the confidence interval. Well, we are 95% confident that the true mean or the true standard deviation of iPod 5th generation iPod music player battery life is between 1.47 hours and 3.90 hours. 3.91 if you round it correctly. Hope that helps.